Once again, welcome to A-Level Physics, Cambridge A-Level. We are now in topic 5, work, energy, and power. So we are now in 5.2, potential energy and kinetic energy. Let's just review what we have done in the previous video. Right, we have defined, basically we are looking at force does work in this topic. And we define the first thing, what is work? Force times displacement in the direction of the force, or distance move in the direction of the force. And if the angle between the force and the displacement is theta, then it's Fx cos theta. Right? This is not necessary. Right? This is only for your A2. And then we say energy is the ability to do work. So anything that has energy, you just let it does work. And we derive kinetic energy formula. Ek is half mv squared. We derive the gravitational potential energy formula. mgh. And we define our efficiency. Right? We have energy input. And there's a device. Energy conversion device. There's energy output. Energy wasted. So efficiency is energy output divided by energy input. That's the output. It's input times 100%. And we can apply it to a particular case where the wooden block, we apply a force to it because the ground is rough. There's friction there, small f, rough ground. And it move a distance x and increase the kinetic energy to delta Ek. So you should be able to write this formula. Work done by applied force, that's the applied force, equals to work done against friction. That's where the energy goes to. The work done, that's the work done against friction. And you increase the kinetic energy, gain in kinetic energy. So in formula form, Fx, the Fx equals to Fx, small fx, plus your delta Ek. Right? In this case, the efficiency, that is the energy output. That's the energy output. The work done by the applied force is the energy input. So that's the efficiency for the system. Power is defined as the work done per unit time, or work divided by time. Then we derive P equals to FV. Okay, let's just carry on. Energy transformation, a constant force, that's a force, right? Increases the velocity of a car from U to V through a distance x, neglecting friction. Mass of the car is m, so that's where the car is moving, and then you apply a force, increase the velocity to v, force is still applied, so you should be able to write the formula. Work done equals to gain in kinetic energy. Half mv squared final minus initial equals to work done. Transformation energy, a ball is thrown upwards with an initial velocity u, that's the initial velocity, reaches a height h with a velocity v neglecting air resistance. Okay, so you move up to that height, that's your h. Then the reach velocity v. Right? Here is high kinetic energy. So there's a loss in kinetic energy, low kinetic energy. As you move up, kinetic energy is transformed to potential energy. Right? That is low potential energy, there's high potential energy. So there's a gain in potential energy, there's a loss in kinetic energy. Right? Initially it's larger, minus your final one, which is smaller, that must go to potential energy, gravitational potential energy. Right? Conversion of energy. If an object moves up a rough slope at a constant speed by a force F and a distance x, right? There's a wooden block or object. There's applied force. There's the weight of the object. There's the distance move x up the top there, or height is h. Right? There's friction. There's your height of the slope or ramp. So you should be able to write the conservation energy formula. Work done by force. That's the force. Where does it go to? Right? You do against friction. So work done against friction. Then you raise it from 0. Right? Let's assume that the object is at 0 height to a height h. The gain in potential energy, or in mathematical form, F times your x is your right? Friction also travels the distance x. Gain in potential mgh. So energy input is always the work done, right? By the applied force. Energy output is mgh. That's what you gain. Wasted is your work done against friction. The work wasted. The efficiency is mgh divided by fx. In collision, we hear sound. The cars are smashed up. So energy transformation, kinetic energy of the moving cars is transformed into sound. Work done in deforming the cars, right? The bonnet, right? That's why you see the car smash up. So that's work done there. Internal energy of the cars and tires increases, right? If you touch where the deformed parts of the car is, you find it warm because there's work done. That is what you call internal energy. Right? Energy inside the material. Right? Tire has to brake, so there's work done against friction. Right? Energy or heat energy. Right? Transformation energy. This internal energy causes a rise in temperature of the cars and tires, and finally loss as thermal energy to the surrounding, increasing the internal energy of the air molecules. How does work done displacement graph look like when dropping an object? Right? Energy transformation. Initially at maximum potential energy, as the potential energy increases, right, you drop an object. Kinetic energy increase with speed. As the speed increases, kinetic energy increases. So total energy at any time, right? Total energy doesn't change, equals to kinetic energy plus potential energy plus work done against friction. If there is air resistant, work done against friction at any height equals to total energy minus potential energy minus kinetic energy. Work done against friction appear as internal energy or as heat energy of the air molecules and finally lost as thermal energy. So if we draw the height, right, number is mgh, m and g are constant, so it's always a straight line. Potential energy depends on height above the ground. Kinetic energy depends on speed of the object. So you throw up the ball, then the potential energy increases. If you drop the ball, then the potential energy decreases. Right? Height above the ground. So that's the maximum height. A ball is dropped downwards, neglecting air resistance. Sketch the graph of kinetic energy potential energy and total energy versus height above the ground. Right? We just roughly know the equation. Total energy is mgh. H is the height where you drop the object. It has zero speed initially. It is at rest. This mgh. H is the height above the ground. So you want to adjust it again, right? To measure from above the ground, from the where you drop the ball. That's your y coordinate. Y, that's your h. They can replace that equation. Right? Your h is just your capital H minus y. Right? Capital H minus y. So capital H, right? H mg capital H minus y. Okay, total energy is mgh. The potential is mgh. H is the height above the ground. As H is above the ground. Measure from the ground. Okay. So it's basically capital H minus y. Right? We don't want this one. We want this value. Right? So expand it. mgh is the total energy and minus mgy. So that's the equation of a straight line. Total energy is your EP plus EK. So as long as we know the potential energy graph, we can get the kinetic energy graph. Total energy is constant, doesn't change. So there's a kinetic energy graph. There's a potential energy graph. Where air resistance is not negligible, total energy still doesn't change, it's still constant. Right? If it's not air resistant, it's that line for kinetic energy. Potential energy is still the same, doesn't change, it depends on height. So it's still a straight line, but the kinetic energy depends on the velocity. So when it reaches terminal velocity, the velocity will start to decrease. So it means the kinetic energy will start to go away from the straight line. And at terminal velocity, the kinetic energy is constant. Right? This part where the velocity is quite small, straight line and low speed. When ball reaches terminal velocity, the curve becomes horizontal. Okay, so let's summarize all that we have learned. Okay, let's try some problem. Solving some problem. Right, let's try review your O-level work. A weightlifter lifts some masses through a height of 1.8 meter. The gravitational field strength G is 10 Newton per kilogram. During the lift, the gravitational potential G of the mass increases by 4,500 joule. What is the total mass of the lift, of the mass lifted? Right? Go to the formula, mgh. So potential energy is given. Mass is what we want to find. G, we are told to use 10. I is 1.8. So it's 250 kilogram. Answer B. If he's holding the mass above his head, is he doing any work? No. No. There's a force pulling it downwards, the weight, due to the weight of the mass, but no distant move. A child slides down a slide. The height of the child is 200. The weight of the child is 250 Newton, and the height of the slide is 7.0 meter. The work done against friction as the child travels down the slide is 1,300 joule. What is the change in gravitational potential energy? And what is the final kinetic energy of the child? Okay. Change in potential energy, basically we are interested in that's the maximum height, that's the ground there. This mgh, right? mg is 250 Newton, that's the weight, times your height, 7 meter, is 1,750 joule. Conservation energy, loss in potential energy is gain in kinetic energy plus work done against friction. Put in all the values given, right? Loss in kinetic energy, that one. Gain in kinetic energy, sorry, loss in potential energy is that one there. And work done against friction is given there. To calculate that, answer is A. What's the kinetic energy of the person? What is the kinetic energy of a person walking? Yeah, the examiner can ask you that. You can roughly estimate it. Take the mass of the person as 60 kilograms. You can remember it good. If not, roughly the speed of 2 meters per second. You calculate out. About 120 joule. Opposed of force of 12 Newton, that's the force, acting at an angle of 60 degrees to the horizontal, that's at 60 degrees. Pulls a pulley on a smooth horizontal surface a distance, this place is 8 meter. What's the work done? Just using the formula, fx cos theta, put in your value, 12 f, x is 8, cos 60, calculate out is 48 joule. A body of mass 0.5 kilogram is projected horizontally, that's your body or object, with a speed of 8 meters per second from the top of a cliff for 45 meter high. That's 45 meter high. What's the initial kinetic energy? What's the kinetic energy just before it strike the ground? We're interested kinetic here and here, where it's before it strike the ground. What's the speed of the body? Direction of the velocity when the body strike the ground. Right? At that point there, what direction of the velocity? We want to find the speed and the velocity. Right? Conservation energy at the cliff top, the body has both kinetic and potential energy. So total energy is equals to kinetic energy plus potential energy. At the bottom of the cliff, that part there. It has, at the bottom of the cliff, all this kinetic energy and the potential at this point becomes a kinetic energy. There's becomes a the total energy initially becomes a kinetic energy at this point, where move down there. Okay, let's calculate one by one. Initial kinetic energy, you should know the formula, half mv squared. Right? Cambridge is very kind. Usually it is from simple to more and more difficult question to build up your confidence. Right? That's the mass. V squared. Okay. So initial kinetic energy, you want the total energy. So kinetic potential. You want the kinetic energy at this part there. And move down. So it is equal to the total energy. So it's initial kinetic plus the potential energy. So we have calculated there. Initial kinetic energy, potential energy, mgh. Right? That's the mass. That mass there. That's the height. And 9.81 you have to use, cannot use 10. Calculate it out. Right? Final velocity. Okay, this is the final velocity. From this formula, kinetic energy, we calculate the final velocity or speed, because we don't know direction yet. Put in there, that's the mass. Now, n v squared. Calculate our v is 31 meter per second. So where's the direction? That's the path we will go. So that's the v that we have found. Okay, direction. That's the third one. Right, let's just redraw it bigger. That's your, doesn't change. Horizontal, there's no air resistance. There's no force applied to that. Only gravity is pulling it down. So the horizontal velocity doesn't change. Right. Can draw it, make it bigger, or draw it on the diagram itself. So that's the angle theta. Right. So we take cos theta, it's 8 over 31. So using calculator, we get 75 degrees. A body of mass 0.8 kilogram move with constant speed 12 meters per second up a round incline of length 20 meters. The plane is inclined at 30 degrees to the horizontal. The applied force is 10 Newton. Write down the work energy equation. That means the conservation of energy equation. Work done by applied force. That's the applied force. Right? Kinetic energy doesn't change because we are told it's constant speed. Height increases, so there's a gain in potential energy. And then we are told it's a rough plane. So that's work done against friction. Right? Formula form. Work done against friction. Gain in potential energy. Kinetic energy of the body. Kinetic energy of the body is just formula. Calculate out. Gain in potential energy by the body, mgh. Right? M is 8 kilogram. G is 9.81. And then you want to find this height. This height there. Right? So it's 20 20 cos 30. Sorry, far away from this angle is sine 30, not cos 30. Cos 30 is this one. Okay, out. Okay. Now we can apply the formula. Work done against friction. Put in what we have calculated as the force, applied force, times the distance moved. That's work done by the applied force. Work done by friction. Gain in potential we have calculated earlier. And calculate our work done against friction. What is the energy converted into internal energy or heat? It's just the work done against friction. Power station has an efficiency of 40% and generates 1000 megawatt of electrical power. What's the input power and the wasted power? Okay, we will find that the answer is donkey. Efficiency is P out. Output power over input power times 100%. So efficiency we are told is 40%. And then output generates, right? Is the output 1000 as the input, that's 100%. Then we can calculate our P in, cross multiply, that's all. So P in equals to P out plus P wasted. There is the wasted power. Power output, power input, power wasted. Calculate out 1500 megawatt. The bicycle dynamo is started at 0 time. That's at 0 time. The total energy transformation by the dynamo during the 5-second increases as shown in the graph. What is the maximum power generated at any instant during the first 5 seconds? Usually, for this case, you have to take the gradient because power is rate of doing work, rate of energy transformation. So it's a gradient. Right? So the largest gradient solution, right? That's the rate of work done. Maximum gradient. That is the maximum gradient. Take 0.4 minus 0.1 divided by that is 3 minus 2. Calculate 0.3 watt. Okay, that's the end of our lecture. We'll use transformation of energy. Right? Mechanical energy transform to electrical energy, transform back to mechanical energy. And that's rotation, mechanical energy. That's the end of the lecture. Good night.